Alright, so this is 6.3 notes. We're going to be learning about vectors. So with vectors, we have magnitude and we have direction. Magnitude is the length of a vector. Direction is the slope. So to find the length of a vector, we have our distance formula. So it's like the distance from one point to another. So our distance formula, which we go back to chapter 1, is the square root of x2 minus x1 squared plus y2 minus y1 squared. And then our slope is y2 minus y1 over x2 minus x1. With our vectors, we have an initial point, which is where we start, and a terminal point, which is where we end. It's written like this. It's a little bit different than array because array continues on forever in one direction, whereas a vector stops at the terminal point, but it does have direction, so it starts at the initial, ends at the terminal. All right, so just like we said before, our vector has an initial point and a terminal point. Its magnitude or length is denoted by these two bars. So it kind of looks like an absolute value, but it's two lines on each side, and that is the magnitude. It can be found by using the distance formula, like we said on the last slide. Two directed line segments that have the same magnitude and direction are equivalent. So two vectors that have the same magnitude are equivalent. So it has to have the same length, which goes with magnitude, and same slope, because direction is slope. Vectors are denoted by lowercase boldface letters such as U, V, and W. So these are common variables, I guess you can say, that we use for common letters that we use for vectors. So you'll see U, V, and W, and it's always the bold one. Bold means that it's vector. And then vectors are also written with these little arrows, like this. So if you see parentheses, this means that it's a point. The arrows means that it's a vector. So if the question asks to list the vector and you put parentheses, it'd be wrong, because parentheses means points. All right, example 1 says show that the two vectors are equivalent. So for two vectors to be equivalent, we need the length to be the same. So that means they have to have the same magnitude, and we need the slope to be the same. So we need to check both of these. So I have vector u and vector v. How do I find the length of vector u? The distance formula. So the square root of x2 minus x1. So we can list it 0, 0 is x1, y1. Q would be x2, y2. So it'll be x2 minus y1. x2 minus x1, I'm sorry. So 3 minus 0 squared plus y2 minus y1, so 2 minus 0 squared. So this will be 3 squared, which is 9, plus 2 squared, which is 4. So it'll be the square root of 13. And then to find the slope, we do the slope formula. So that'll be the change in y's over the change in x. So y2 minus y1, 2 minus 0, over 3 minus 0. So this will be 2/3. So that is the distance and the slope for u. Now we have to do the same thing for v and check and see if they're the same. So for vector v, I need to find the distance, so I'm going to use the same formula, square root of x2 minus x1. So this is x1, y1, x2, y2.
Does it matter which one you put?
It will, because you have a terminal and an initial point, so it will when like finding the component form of a vector, so it will. All right, so we have 4 minus 1 squared plus 4 minus 2 squared. So 4 minus 1 is 3, and 3 squared is 9. 4 minus 2 is 2, and 2 squared is 4. And 9 plus 4 is 13. So our distance is the square root of 13, which is the same. And then we have to find the slope. So slope is y2 minus y1 over x2 minus x1. So this will be 2 over 3. So are these two vectors equivalent? Yes, because they have the same distance, same length, and the same slope. All right, so here it says that we commonly see vectors that start at the origin. This is standard position. So standard position, initial point is at the origin. And then again, here we see our vector that's written with the little arrows. All right, so here we have the component form of a vector, which is just like the basic form that it's written in. So with the arrows, that's our component form. The component form of the vector with the initial point P and terminal point Q is given by this formula here. So we can take 2 points and subtract them to find our vector. We always subtract terminal minus initial. So it's always terminal minus initial. And then to find the magnitude, we use our distance formula, which is what we've been doing. But once you have component form, you can just square the first one and square the second one and add them together. So if you have your vector that's in component form, you can just square them both, add them together, and take the square root, and that's your magnitude. All right, example 2 says find the component form of a vector and the magnitude of vector v represented by the directed line segment that has initial point and terminal points. So it's always terminal minus initial. And then it helps to remember that first goes with first and second goes with second. So terminal minus initial.
And what's that to find the component form?
The component form. So first, our terminal point would be -1. minus initial. So the x in our initial would be 4. So -1 minus 4, which would be what? -5. And then we have terminal minus initial again, so that would be 5 minus -7. What's 5 minus -7? 12. So the first point goes with the first point, second one goes with the second, and it's always terminal minus initial. So this is our component form. And then to find the magnitude, once we have it in component form, we can take the square root of the first one squared, so -5 squared, plus the second one squared. So this will be 25 plus 144, which is 169. And what's the square root of 169? 13.
Do you have to do plus or minus?
No, because it's length, so length is always positive.
And then what's underneath the V and the 5?
So this is just saying the magnitude of V is 13. We can perform operations with our vectors. So we can multiply our vectors by a scalar, which can just be any number. So if we multiply by our scalar, it changes the length of our vector, but doesn't change the direction that it goes in. So
Can I take a picture of example?
yes. So here we start with vector v. If we multiply it by 1/2, it cuts it in half. If we multiply it by 2, it doubles in length. If we multiply it by a negative number, it changes the direction. So notice that our arrow is now going down. So our initial point becomes our terminal point, and our terminal becomes the initial. So if we multiply by a negative, it changes the direction. We can add two vectors together. So just remember, when adding, the first goes with the first and the second goes with the second. So you would add the first two numbers together and add the second two numbers together. So we'll do an example. This one's kind of just showing you that if you have the two vectors together, you can just like put them on top of each other. So notice here how we have u, and then from the terminal, then we put v right there. So we technically move v up here. And then our new vector would be from the terminal of the first to the initial of the second. So it would be this. So, yeah. Okay, so if we have vector u and vector v, we can add them just by adding the first numbers together. So the first goes with the first, and add the second numbers together, so the second goes with the second, and then that'll be our new vector. So just add the first ones, add the second ones. And then if we multiply by a scalar, that scalar gets multiplied to both numbers in our vector, so just think about it as distributing. It has to get multiplied to both of them. So same thing when multiplying by a negative. So if we had a negative v, it just, think about it as distributing, so it changes the first number in our vector to be negative and the second. And then same thing with subtracting. If we had u minus v, you can think about it as adding a negative, but it's the same thing as subtracting. So subtract the first two, subtract the second two. This slide shows you what it looks like when you subtract two vectors. So instead of like taking v and putting it the initial on the terminal of u and having it go that way, we actually change the direction when v is negative. So instead of going that way, you're now going that way. So it's just visualizing what happens when you add the two.
What does that mean?
All right, so example 3, we're actually performing our operations. So on WebAssign and probably on your test, you'll see kind of questions like this where it'll give you multiple vectors, but the operations, you'll only use certain ones. So it will help to write down which one you're using because it could give you 3 vectors and only ask you to add 2 of them. So I would write down v. So I have 2 times vector v, which is -2, 5. And when multiplying by a scalar, we just distribute. So our new vector v, 2v, is -4, 10. So we just distribute. For b, we're subtracting our vectors. So we start with w, so that would be 3, 4, minus vector v, which is -2, 5. So remember, first goes with first, and we subtract. So it'll be 3 minus -2. And then second goes with second, and we subtract. So 4 minus 5. So what's 3 minus -2? 5. Because minus a negative turns into a plus.
So you're not foiling, you're just doing first and last, basically?
Yeah. And then 4 minus 5 would be -1. So this is w minus v. And then the last one, c. We have v plus 2w. So this will be -2, 5, that's v. And then plus 2 times w would be 3, 4. What do you think I have to do first? Distribute. Just like our order of operations, we have to multiply first. So this would be -2, 5 plus, now this is 6, 8. And we add them together. So the first one goes with the first. So -2 plus 6 is 4. And then the second goes with the second. So 5 plus 8, 13. So our new vector is 4, 13. The last page talks about vector operations. So they're pretty straightforward. Like if you have u plus v, it's the same thing as v plus u. So when adding, you could change the order. If you add 0 to a vector, it's the same vector. If you are multiplying by a scalar, you can multiply, if you're multiplying by 2 scalars, you can multiply the scalars first and then multiply them to the vector. If you're multiplying both vectors by the same scalar, you can distribute. Here, if you are taking the magnitude of a vector times a scalar, you can separate them, find the magnitude first, and then multiply it. This one, you can change the order when adding, so you can add these 2 first, or you can add these 2 first. Doesn't matter when adding. If you add a vector, and I guess subtract it from the same vector, you get 0. Same thing when multiplying by 2 numbers added together, you could distribute. And then if you multiply a vector by 1, you get the same vector. If you multiply a vector by a scalar of 0, you get 0. So pretty self-explanatory. The last thing that I wanted to talk about is linear combinations. So we have a vector in component form, which we can say is, I'm going to make one up, so like -5, 3. This is component form. In linear combination form, we would write this as -5i plus 3j. So this is linear combination. So you'll see some questions on WebAssign that'll give you the linear combination and ask you to write the component form. So you're just taking the coefficients of I and j. And it uses the variables I and j each time. So I is the first one, j is the second.
And you don't put the arrows?
Not in linear combination form, no.
So you literally just put an I and a J behind them?
Yeah.
Yeah.
So if it gives us the linear combination, let's say I minus 2j, what would you say our vector in component form is?
-1. Oh, probably
1
1. Minus, and then -2.
and -2.
What is an I times I?
The I doesn't have a negative in front of it, so it's just 1. So it's just like having an x, like our coefficient in front of the x would be 1. So if it's just an I, it's a 1, and then the negative sticks with the 2, so -2.